So today's ghost day. What we're trying to do is we're trying to do an integral with a heavy degeneracy and a constraint. So our starting example is if we had this simple integral e to the I s of x and y, where the symmetry is that s of x and y is really just a symmetry, depends on the radial coordinate, so the angular coordinate is irrelevant. And we're going to do it with a constraint because that's what we're trying to do. It's a bit of a overkill in this case, but we're going to imagine putting some constraint g of r equals to 0. So this will take some line here, and so we're doing the integral over all space. The symmetry is the theta angle, and here's g of r equals to 0. Okay. We can parameterize the degeneracies by letting r theta, that's r sub theta, be r phi plus theta, where theta is some parameter. And then we'd like to motivate the constraint that 1 is integral d theta delta of g of r of theta with the extra feature that's dg d theta. Okay. So what is this? First of all, the g of r of theta is just basically the same constraint rotated by an amount theta. So there's theta, we rotate it by a little bit. That's another equally valid constraint. All of those thetas are equivalent. To do this identity, we use that if I have some integral dx delta of g of x, that's 1 over the absolute value of dg dx evaluated when g is equal to 0. Okay, so if I just multiply through, this is evaluated here when g is equal to 0 because there's a delta function there. So that's an identity. So if we insert that, we get w is the integral d2x d theta dg d theta delta of g of r of theta e to the I s of r, which I can then write as integral d theta of some w of theta, where w of theta is the constrained integral, d2x dg d theta delta of g of r of theta e to the I s of r. So the beauty of this, such as it is that this is now only one copy. So instead of doing all these different copies, different thetas, we only have one of the copies, so it's constrained. And it's independent of theta just by the symmetry. Okay, we can't quite throw away theta yet because there's this dg to theta piece here, which we have to end up calculating. But if it's independent of theta, then I've just factorized out the symmetry. In this case, it's just a factor of 2 pi, but in the case of that we're really doing, it's going to be a factor of infinity. So it's nice to factor out infinities if you can, and then we're done. Okay, so that's the plan. We're going to do this for the gauge symmetries. So I need one more generalization of this. So here's how to do a constrained integral for one constraint. We, of course, will have an infinite number of constraints because we have constraints at each point in space-time. So how do you do more constraints? Okay, we're going to insert the operator 1, which some variables, du1, du2. I'm going to do 2 here. You get the pattern. There'll be a delta of some function of u1, u2. Another function, delta function of f2, u1, u2. These, when we do gauge series, will be constraints at each point in space-time. And then instead of the dg d theta piece here, we need something, delta. And the point is that we have to figure out what is delta. It's not that hard. It's just a Jacobian. And this, in a way, is the Jacobian of a one-dimensional transformation. So we have, so let's just, to figure it out, let's just set x1 is f1 of u1, u2. x2 is the other f2. Then if we have integral dx1 dx2 for any function f of x1, x2, that we convert over to du1 du2 f of f1 u1 u2 f2 u1 u2 times the Jacobian. So that's just the general transformation. And the Jacobian is just the determinant of df1, du1, df2, du1, etc. It's the determinant of that. It's the determinant of df I duj. And so if we basically then just apply the change of variables where our function is delta function, and we end up with identity 1 is the integral du1 du2, the determinant of df I duj delta of u1, I'm sorry, that's the f1 delta of f2 of u. Okay, so that's just how you do the change of variables. With many of them, we're going to want to do one of these for each point in space-time. So again, we're going to be faced with the dreaded determinant of something over all points in space-time, but we'll survive. Okay. So any questions about it? So if there are no questions, I'm happy to take them, but let's do QED first. Basically, what we're going to do is have the path integral, and we're going to want to imply some constraint. The constraint will be some f of a mu equals 0. Okay? There's a bunch of gauge copies then. We have a mu goes to a mu. I'll put a theta on it, just because that's our notation. A mu plus d mu theta of x. So there's the gauge. That's the symmetry. But this is an infinite, big infinite family. When you're doing the path integral, you sum over all possible a's. All of the a's that are related by this give you exactly the same result in the path integral. So path integral is the same for each of them. So there's certainly an infinity in the path integral. Now, sometimes we can live with infinities in path integrals. We do it all the time. This one seems to give us trouble because it's much easier if we fix the gauge, so you stop this infinite family, and then live in a constrained integral. And so we're going to try doing that. So let's constrain the integral. So here's our formula. 1 is the integral over all these thetas. Okay, this itself is an infinite dimensional integral, so it's like a path integral itself. You integrate over all the possible thetas that you can imagine. You're going to impose this delta of f of a theta. So the constraint is going to be that it's equal to 0. And then we've got some delta of a, which will calculate. But it's really, we can already see that it's the determinant of the of d f d theta. Okay, we'll come back and do that, but that's what we're after. So let's do that. Okay, let's just see how it's used first. To use this, we've got some generating functional, which is the integral over all the gauge fields, the path integral, e to the I, integral d for x, the Lagrangian of QED, maybe, and then a J mu A mu piece. So you add a source if you want. We will now add this identity dA, d theta, delta of A, the constraint delta of f of a of theta equals to 0. And then I've just put in unity there. Let's just assume, I'll prove this in a minute, delta of A is independent of theta. Let's do this in just a second. Then we can factorize out the d theta the integral d theta, which of course is infinity, and leave behind the constraint. So we end up with z is some number integral dA delta of A, the constraint and then e to the I integral d for x Lagrangian plus JA. And so now I have just the constrained integral. Okay, so if we look at this, this is what we've always done. This is what I would call naive gauge fixing. That's where you just impose a constraint. You say, I'm going to work in Lorentz gauge. I'm going to impose this constraint. And there I've imposed it. We've seen that by taking a little extra care, we get this extra feature here. So let's call this rigorous gauge fixing. There's one where we've not made any approximations in doing it. So we've learned already something, that our old style of just fixing the gauge and proceeding is potentially incomplete. Okay. So let me go back and just make this argument that the Jacobian is independent of A, because this is a very general feature. And in fact, all this is general. I'm pretending I'm doing QED here, but I'm doing all the theories all at once here. This is any constraint. Show that delta of A is independent of theta. Well, it's a little bit of a fussiness. It's basically what I just said above, is that they're all related by symmetry, so they're all the same. But let's just do someone. So here we have delta minus 1 of A is the integral d theta delta f of A of theta.
Where did the delta inverse?
Okay. Did you ask a question there?
Yeah. Why is the inverse there?
Oh, I just pulled it out. Remember, my identity had 1 was equal to it with it inside the integral.
But doesn't this already assume that delta is independent of theta?
Yeah.
Because you pull it out of the
integral. Actually, well, there's a constraint here. It's actually the theta dependence here is that this is evaluated with f of A theta equals to 0.
But
yeah. So, am I assuming something? Yeah. So let's just look at the proof and just see what's. goes on. It's just basically that if I let if I shift it by some theta 0 and let theta 0 plus theta equals theta prime, if I had delta minus 1 a, let's make it theta 0 now, it's where I've shifted it a little bit, equals the integral. I'm going to assume that d theta prime is d theta. So I'll just make this d theta prime delta of f of theta prime. Yeah, I've skipped a step. So let's just go back here. Here's what I'm really saying is if I shift this by theta plus theta 0, shift it by a bit, I can then just convert this into theta prime. It's an argument like all path integral arguments that the sum over all thetas is independent of a shift. It's not much of a proof, I guess. But I'm going to use the fact that it is. Maybe it's easiest just to calculate it. Okay, so let's actually do this for QED. So let's take a typical constraint. Here's f of a. I could take is d mu, a mu minus a constant, for example. Any constant works. Then the gauge transformation is f of a of theta is d mu a mu minus d mu theta there minus f is d mu a mu minus box theta minus f. So our determinant that we have there, delta, is the determinant of df d theta. Df d theta is box, so the determinant of box. So it goes over all points in space-time. Now we're no longer scared of determinant of box because we did the determinant of box plus m squared as an evaluation earlier, and we had fields in there. In this case, it's even less scary because there's no A dependence. So it's just a constant. Okay, so in the case of QED, the det is a constant, and the naive approach works. Okay. So we can just proceed by just writing out without this constraint. So z j is the integral dA delta d lambda a mu minus f e to the I integral d4x. We have a mu. I'm writing the Lagrangian. It's a half a mu box g mu nu minus d mu d nu a nu plus j a mu. And so since d mu a mu is just a constant, these guys just become constants. So we don't have to worry about them. And then I can operate with just box and not consider those guys. Okay. So this gives you your usual Fineman rules. The rule was minus I g mu nu over q squared plus I epsilon. Okay. At this stage, so that's the gauge fixing for QED. We've not done anything particularly different. One thing I do want to do here, I don't want to miss the opportunity to do covariant gauges. Okay. I'm actually not going to use this in gravity because the gravity is complicated enough with just the usual harmonic gauge, which is the simplest possible gauge. But no point to missing an opportunity to do covariant gauges here. Then the issue is the following. So basically, I'm going to do gauges that are related to Fineman gauge or Lorentz gauge by a parameter. We'll have a continuous family in this case, and you will be able to change the propagator and change the Lagrangian. I guess I do this trick. I do this trick in gravity. Yeah, so let's do the following. So we had the constraint that d mu a mu minus f equaled 0. That factored it into this well-behaved piece and a constrained integral. We could have used, let's imagine if I used f of x. So a mu is a function of x. I could use f of x, a different constant at each point. And in fact, I can do even better. I can do a whole family of those. So here's another choice. We have the integral df. I'm integrating over all of these. Delta of d mu a mu minus f of x. And I'm going to integrate with some weight e to the I over 2 C integral d4x f of x squared.
C come from? Why is he frozen?
Just a second, I'm just trying to connect my other computer.
What? I think, but that entire
Let's
thing
see
is.
if this works. All right.
Everyone see plus.
Get the other computer then. Okay. By inserting that, it's the equivalent of inserting e to the I over 2c integral d4x d mu a mu squared.
Is that an I? 2C in the first one, or was it a DDC? That's next one.
Okay, so by doing this extra constraint, I now have my path integral z is integral dA so I've now taken the constraint and basically exponentiated it by doing this extra trick. I have e to the I integral d4x. My usual Lagrangian after integrating by parts is box g mu nu minus d mu d nu a mu. And now I've exponentiated this piece. I now have a new piece here, which is minus 1 over 2c d mu a mu squared so now instead of the delta function sitting down there, the delta function I've exponentiated in that form. So any of these are equally good. I mean, I've just put this up with any parameter. So all these are completely equivalent. But this guy here then modifies the equations. And in fact, if I just integrate that by parts, this turns into 1 over 2c a mu d mu d nu a nu. So it looks just like this other piece that we have here. This has an inverse. The Feynman propagator for this theory in momentum space is I over q squared plus I epsilon minus g mu nu plus 1 minus c k mu q mu, sorry, q's over q squared plus I epsilon. And so there's my parameter c. So these are covariant gauges or R sub c gauges. C is a free parameter. an incredibly powerful constraint. If you calculate with this C, this thing had better drop out at the end. Okay. Now, it's actually relatively easy on tree-level processes. If you're doing tree-level processes and you'd use this as a propagator, then basically Q dot the vertex means that this piece drops out. So that's the easy part. It's not at all clear when you're doing loops and you use it in a loop like that, that it's going to drop out. So it's a incredibly powerful constraint. Okay, so see, if I didn't have this extra operator here, it'd be like taking C goes to infinity. You can see that the df blows up. Okay, so it blows up because of that. C equals 1 is the usual Feynman gauge. And you can see this then in the path integral, and I can see I forgot a factor of a half, so let me stick it in at the end. There we go. There's a half there. I had it in a previous one. There it was up there. I got it, so I'm not cheating. It's really there. But if you take C is equal to 1, then you can see that, so I've integrated this by parts. There's a plus there. The new piece cancels off the derivative piece, and I start off with the Lagrangian then. So the Lagrangian is then Z in Feynman gauges d a mu e to the I integral d for x 1/2 a mu box a mu plus j mu a mu. And so by doing it this way, I've simplified my Lagrangian. So it's not just that I've fixed it on the equations of motion, but I've changed the Lagrangian. So to be honest, that's actually what we're going to do when we do general relativity next time. We'll do this for harmonic gauge just by straight exponentiation. And we'll simplify the Lagrangian so we have a simpler place to start from. Okay.
John?
John? Yes, I'm sorry. I'm answering a question here. Let me just, he was asking if the infinity gauge is Landau gauge. No, Landau gauge is Feynman gauge. Don't work with Z equal to infinity. There's in non-abelian theories, it's sometimes unitary gauge. I think I could be wrong. I'm sorry. Okay, Dartmouth guys, was there a question?
Yeah, actually, could you just summarize what the benefit of this covariant gauge, the introduction of the psi parameter is? I actually just don't get that. Okay,
so there's two benefits. One benefit is that I've simplified my Lagrangian. So instead of having a Lagrangian like I had up here, where I had a delta function sitting down below, and I sort of just threw out some terms by hand, I now have changed the Lagrangian and made it simpler, and I no longer have that delta function.
Okay.
That's good news for when you were doing some more complicated theory where I can't as visibly throw out those gauge copies just by hand. Doing it this way, I simplify the Lagrangian. I've got rid of my delta function. I'm golden now for the rest of the way. So that's one advantage, is just as it's a more beautiful way to do it. The second advantage is that if I wanted to do these covariant calculations where C is a free parameter, I can do that, and I have then checks on my procedures, because since it's a free parameter, it should drop out from all observables. And if you're doing a not so simple calculation, this is an incredibly powerful check that you've done the calculation right. If you miss a minus line, you're not going to get, between two diagrams, you're not going to get C canceling out. You have to get all those factors right to get it independent of C. So people who do professional Feynman diagrams often like that part of it. Okay, but for us, when we're doing gravity, I'm going to use a trick like this to just simplify the Lagrangian by taking harmonic gauge. I'm not going to keep it as a free parameter because it makes the propagators too painful, but I'll simplify the Lagrangian. So does that answer the question?
Yes.
Good. Okay. Now here we come to Fadeev and Popov. Okay, so in general, we lucked out in QED that determinant of the gauge transformation vanished, or it was a constant. It doesn't in general vanish. And so we're left with this determinant there, and we have to figure out how to deal with the determinant. And Fadeev and Popov use the following trick. If you take a fermionic path integral and you take integral d psi bar. So here's my typical fermionic path integral, e to the I integral d4x psi bar, some differential operator psi. That gets evaluated as the determinant of the differential operator. Okay, remember for bosons, it was 1 over the determinant. It was actually, if it was a real boson, it was to the 1/2 power. Complex, it was to the 1 power. So let me do that. But this gives you the determinant upstairs. Okay, so that's, we're going to invert this. We're going to then take, we have to take the determinant of df d theta, and we're going to write that as the integral over some variables. So I'm going to use C, dc, dc bar. These are fermionic variables. E to the I integral d for x, c bar, df d theta, c. So these c's are, they're fermionic. These are the ghosts. By doing this, there's no source coupled to them. And so that implies that they're not you don't form matrix elements with it. They're internal only. So you don't take them as external states. So these will exist in loops. But not much else. Okay. So there's the Fadeev Popov trick. You have this determinant. You exponentiate it with fermion fields. Okay. So if we do QED again, we had df d theta, and so z then would have been integral dA dc. Okay, df d theta was box dc bar e to the I integral d4x, Lagrangian, whatever pieces you want. But then we now have e to the I integral d4x c bar box c. Okay. This thing factors out as before, but you can start to see that it's looking sort of like a wave equation up there now. So now it looks like a particle with a wave equation. So we can live with this. Gives us hope that we can live. Okay. So the place where it clearly plays a role is Yang-Mills theory, QCD. So let me do QCD, where it's a non-trivial example. Okay. So let's do non-abelian Yang-Mills theory. Now, I did Yang-Mills theory in one little 10-minute stretch at the first day of class, maybe second day of class. So I'm going to review it a little bit here. Let me just, because what I need the gauge transformation, and then I'll impose some constraints. Okay. So remember the gauge transformation was psi goes to u of x psi, where u in general is some SUN matrix. Let me do SU2 for my example, so because I have to do an explicit calculation. I'll do SU2, then I'll just tell you the answer. SU2 u is e to the minus I alpha I tau I over 2. Alpha is a function of x, and tau I are the Pauli matrices. The SU2 matrices. Okay. The covariant derivative was d mu plus I, some coupling constant, tau I, AI mu over 2 in my normalization, which was d mu plus I G. I wrote this as a matrix when I used double bars underneath it. A double bar is tau over 2 A mu. Okay. I then imposed that I wanted d mu prime psi prime equals u d mu psi, so that it transforms the same way as psi. which then imposed that d prime u is u d mu u minus 1. And then from that, derivative has the usual derivative in A. We got our transformation on A. So A with the matrix is transforms as u a u minus 1. That's the prime. And then plus I over g d mu u u dagger. Okay, so that was my lightning review. Okay. But basically, there's my transformation property that I want. Actually, everyone comfortable with it. I have to work out two things. I have to work out the gauge transformation of this for small transformations. In some ways, the easiest part is the gauge part. I'm just taking the derivative of this matrix, and I'm going to work the first order. It's pretty easy. The piece that's a little harder is that piece. So let's do this for small transformations. I'm going to take u is 1 minus I over 2 alpha dot tau. And so then A prime, which is tau dot A prime over 2, is 1 minus I over 2 alpha dot tau. Now let's put a tau dot A here. Over 2. 1 plus I over 2 alpha dot tau. And then, as I said, the derivative piece isn't too bad. It's then just plus the i's cancel 1/2 d mu alpha dot tau. Okay, that first piece then is just tau dot A mu over 2. And then the second piece, part of that is minus I over 4 alpha dot tau commuted with tau dot A. Okay. This commutator turns into 2I epsilon I j k alpha I a j tau k. All right, I'm essentially done. Basically, now I want to write out what A mu prime I is AI plus, well, okay, I'm missing a 1 over G here, so sorry. Let's go back up here. There's a 1 over G in the derivative piece. I have 1 over G here. Okay, so I get 1 over G d mu alpha I. And the second piece is minus G epsilon I J K A J alpha K. If I did my signs right. All right, so here's my gauge transformation. That's the piece that I was working for. And in general, this turns into these Fijk symbols, which are the general structure constants in SUN. So in SU3, they're the SU3 Fijs. Okay, well, at this stage, we can calculate we have the invariance here. We can calculate the change in this determinant. Okay, so let's take our constraint as some f of a mu of theta. Theta is here, our parameters alpha I. We're setting that equal to 0. And let's take that to be something like d mu a mu I minus f equal to 0. So you use the gauge just equivalent to what we did in QED. Except that here I now have to take a of theta because I'm taking this function a of theta. So I do the gauge transformation. That's then the derivative a mu minus or plus 1 over g d mu. Okay, I'm calling it theta here, so let's just call it theta I minus f or g Fijk a j theta k. Okay, so basically, remember, I'm trying to do a gauge transformation and look at the theta dependence to get this term. And I'm sorry, I am missing something. I'm taking the gauge transformation of A, but I'm taking I have a derivative on it from the gauge constraint, so I actually need a d mu here. The piece I wrote out was just that.
What is that?
Okay. So now we have
No, the second term.
we have d f I d theta j equals, well, the first piece is just a delta ij box, which is basically the same thing as we had for QED, the two derivatives on theta. I have a 1 over g floating out in front. And then the second piece is minus g Fij a, the derivative acting on a k mu. Now, just like this derivative acts on everything to that side, this derivative acts on things to the side too. So when we exponentiate it, I'll make a comment there. So it's not just the derivative here acting on A, it's actually acting on whatever comes to the right of it. Okay, so now our gauge, our determinant, has a dependence on A. So it's not trivial. Now when I do the exponentiation, I have my ghost Lagrangian, which, remember, was C bar. Well, here there's one for each of the constraints. Each of the constraints carries something. So it's called Ci delta ij box minus G Fij d mu A K mu Cj. Okay, so now my ghost Lagrangian is not trivial. I've got an interaction here with the A field. Okay. As I said before, let me just clarify. This derivative acts on A and C. So you can integrate by parts. And make it the derivative on C bar, AC, if you want. You'll see that in the Fineman Rule, so I'll give you in just a minute. And the other thing I've done here, I have rescaled so I had 1 over C, 1 over G, C box C. I've rescaled the C fields by a constant to put it in normal normalization. C bar box C. Okay, I've just changed the normalization of the fields to make the kinetic energy piece look normal. Okay. So, what have we got? Okay, so we now have this ghost Lagrangian. We've added this in place of that determinant with non-trivial interactions. Remember, C's are fermions. Okay. This has a major effect when you do the calculation. There's a -1 for any closed fermion loop. This goes back to our usual thing. This subtracts out a loop, portion of a loop. This is why Feynman did it. So it takes away part of the loop. That minus sign is crucial. So we'll have closed loops of these ghost fields. We also have a interesting feature. This is a fermion, but its propagator is not going to be the usual Feynman propagator. We have C bar box C. So when you go to use this as a propagator, the propagator is I delta ij, so here's over p squared plus I epsilon. Okay, so p squared instead of p slash for normally for fermions, but that's what you get when you try to invert that, so that comes out. And then there's the Fineman rule. Okay, well actually let's make it this way. I'm using dashed lines for the ghosts, gluons. Actually, given the time, I'll just skip to writing out what that Fineman rule is. Let's be explicit about it. If this is momentum P coming in, Q coming in this way, R going out that way. So PQR. And I'm labeling this thing A, B, C are the colors. And the Fineman rule for this is G, F, A, B, C, R mu. Okay, so it's the outgoing fermion's momentum, not the incoming fermion's momentum. And that comes from this trick up here. The derivatives acted on both those, so integrated by parts. And I assume I've got my sign right. Okay, so the most important application is in the vacuum polarization. Let's imagine I've got some loop like that. I have to add to this the ghost loop. With of course a minus sign that comes from there. So you add those two together, and that's then your set of Fineman rules. Every time you have the closed gluon loop, you can have the closed ghost loop. And then so there's your ghost loops. And then the last thing to do to get real QCD, you tend to go to these covariant gauges. And so the final result for Yang-Mills is Z of J, maybe some fermion sources. I'd have integral. Let's write out QCD. So here's dA. If we added fermions, we have d psi bar. We have to add these ghosts, dC, I, dC bar, J. I then have e to the I integral d for x Lagrangian, and let me just take that on a separate line. The Lagrangian then is minus 1/4 f mu nu. If I've done the covariant gauges, I have 1 over 2c d mu a mu squared. I then have psi bar I d slash minus m psi, and then my ghosts are dCA, d mu CA minus G FABC d mu C bar A B C C. So that was the ghost part there. So that's quantized QCD done right. The only thing I actually neglected to mention or to emphasize is that in these cases, these ghosts CA transform like an octet in QCD. They're, in general, it's the adjoint. Because they carry the same indices as the gauge fields. All right. Good. I got to exactly where I wanted to end today. That's great. In fact, next time is quantizing gravity. We've got all the tools. It should go really quick. One day, maybe a day and a half at maximum to quantize gravity.